Do do ba ba ba, shoobity bitty bitty ba ba ba, lefty right plus righty left. Oh, do 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 do. Low to high minus high to low. That is what it's all about. It's so great. It's so brilliant. It is all I want to do. Ba-da-ba. Oh, hi. How you doing? I was just sketching a sine curve. You know, I always have trouble with the left side. As you can see, that right side is looking quite top-notch. See what I'm talking about? Right over here. Look at that curvature. That positive slope, that peak, that negative slope, that valley. Well, I'm at it. I figured I'd just sketch a cosine curve, you know? And I'm starting to think that there's maybe a missing piece in this whole deal. We got the sine curve. We got the cosine curve. At this point, we understand what's going on, the relationship between sine and cosine as far as derivatives go. But what else can we find out? Because I know, you must be thinking that. What else can I know about this green curve, about this red curve? Speaking of, I hope you're getting pretty good at sketching these graphs, this sine and cosine. So perhaps you're thinking this question. Can we differentiate trig functions with the quotient rule? Can we make it even more complicated? Okay, I know. Maybe you're not thinking that, but maybe you're thinking this question. Because if we know sine, if we know the derivative of cosine, I mean, we got to figure out the derivative of tangent and cosecant and secant and cotangent. Okay, fine. Oh, all right. Probably you're just thinking this. You just want me to prove it, that the derivative of tangent x is whatever the derivative of tangent x is. Okay, fine. I will prove it. And let's go ahead and differentiate some trig functions with the quotient rule. So here it is. Here's the first example. Find the derivative of y equals sine x over cosine x minus 2. Now, just a quick note on this cosine x minus 2. That's cosine x minus 2. So it's a vertical transformation of cosine x down 2 units. So if that was inside the parenthesis, or if that was being evaluated by cosine, it would be inside of a parentheses with x. All right. Since we could get very confused with the quotient rule, let's set up a nice simple table here and enter the function information. And I'm using a color-coded system for you. How about that? And I'll do like a little abbreviations, high and low, and d high and d low. I figured I'd keep the yellows on the top and the reds on the bottom. So we differentiate the high, and the high is cosine x, so d high, and this is sine x here. All right, sweet. And the derivative of the low, cosine x, the derivative is negative sine x. So that goes right here. How about it? Okay, and then we got cosine x minus 2 right here. And that's a beautiful table setup. All right, now, you know what I'm going to ask you to do. You know what I'm going to ask you to do right now. Get ready. La 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 la. 3, 2, 1. Low die high. Minus high die low, over low, low. Now let's increase that pitch a little bit. Low. Just kidding. Cosine x minus 2, that's your low. Cosine x, die high, minus high. I use parentheses, die low. You just start to see some things happening here, and you might have some expectations of what this would look like at the end, and ultimately you might have some anxiety about remembering some analytical trig and working out things with formulas and stuff. But we'll simplify as best as we can here. But a quick summary so that you can see it. Low, die high, minus. I put that minus with the sign. It's like that. It's giving the sign a value. The sign a sign? How about that? Low die high, minus high die low, over low low. Okay. There's not much else to this except for just doing some algebra here, and we get cosine x, cosine squared x, minus 2 cosine x. And then those signs become positive, so we get a positive sine squared x. Oh, were you expecting this to happen? Maybe. And then we get the same thing in the bottom. At this point, you might start to wonder, oh, maybe there's something else going on and we're going to have two different things. Like, is that some sort of property in the denominator? And I'm pretty sure it's not. But what we see in the numerator is we have the Pythagorean theorem going on with cosine squared and sine squared, which is just, tell me, 1. And by golly, I think we found the derivative of y, which is either written as y equals, or I'm sorry, dy dx equals, or y prime, and that is the derivative. So, not too bad, but what we should expect with trig functions when we take the derivative is we'll be using some of our analytical trig skills and some of the formulas that we've learned in the past so that we could just write it in its simplest form. Because then when we evaluate and we write tangent lines equations of, then we could get the simplest values that can represent the slope. Let's set the table now. Let's switch gears a little bit and create a table for all of the 6 trig functions and their derivatives. So I want you to jot this table down, and on the top row, we're going to set up just the actual functions. So I'll give you a moment to create this table. It doesn't have to be as fancy as mine, but as you're doing that, I'll just remind you that the derivative of sine x is cosine x. And that proof is done by taking the limit of the difference quotient, and that's usually in most textbooks. We know that the derivative of cosine x is negative sine x, but that's all we know so far. We'll come back to this in a moment. I'm going to prove that tangent x, the derivative of tangent x right here, and then we'll use the same idea to fill in the rest of them for secant x, cotangent, and cosecant. Alrighty? So here we go. So that table we're coming back to. Calculate the derivative of tangent x with respect to x. Back in the 90s, I tried to just memorize all of these rules, but the most amazing thing about taking the derivative of tangent x or some of these other trig functions is we could rewrite them. So now I could say, or what you could do is take the derivative of sine x over tangent x. What? Sine x over cosine x. And then all of a sudden we have two functions that we could differentiate and use the quotient rule. Oh, see, here it is, that same question you've been wanting to get satisfied is combining trig functions with quotient rule. So this one's coming at you quickly. Dy dx equals low, die high, minus high, hello, die low. Over low, low. Here we go, go, cosine squared x. I'm going to write it like that. Kind of skip a step. I hear what you're saying. It's like these expressions keep getting more beautiful and beautiful as we go, don't they? Here comes the Pythagorean identity that we were hoping for. Maybe you knew it. I don't know. So cosine squared x plus sine squared x over cosine squared x. You may already know this. I think you probably already know this. And that is equal to secant squared x. This is probably going to be one that will be really easy to memorize for you. May not seem like it at first, but because of this action and because of the simplicity of the process, it will come to your forefront. The forefront of your memory. Well, what do we do now? Well, let's just add it to our list, yes? Let's go back to our derivatives of 6 trig functions here and plug in what we know about tangent. So here's the deal now. Now that we know tangent x, let's analyze that function a little bit and see what we could expect from cotangent x. So we'll take a graphical approach. We're not going to prove it, but just a quick sketch of tangent. And we see that the slope of tangent, slope, is positive. So I'm going to do cotangent in red, and cotangent actually, so let's see here, this is pi over 2, pi over 2. Go a few tick marks further, 1, 2, 3, 4, and cotangent actually has a negative slope, and goes through the point pi over 2 comma 0. So it looks something like this, or this, or this. So all the values and the asymptotes of tangent and cotangent at this point is not really my concern. What my concern is that I look at the green graph and I see, positive slope. And I look at the red graph and I see, negative slope. So we go back to the table, and the derivative of cotangent x must be negative. And it happens to be negative cosecant squared x. You see, cosecant squared x is actually a positive value because it's cosecant x squared. So negative, it makes it a negative slope. And now I see a pattern, that the derivative of the co-functions are negative. So I'm just going to give you this one for now, and maybe we'll prove it later. The derivative of secant x is secant x tangent x. Jot that down. And if the derivative of tangent is secant squared and cotangent is negative cosecant squared, then I'm expecting that cosecant x will be co-functions, so it happens to be cosecant x cotangent x. So that, my learning earthlings, is the derivative, or are the derivatives, of all the 6 trig functions. They seem daunting at first, but they are not too bad. The more we analyze them in different ways, the more that we'll remember them, and the more exercises we try, we will get familiar with them. Alrighty, so the question I have for you then is just thinking about how you will remember all of those 6 trig functions. There is space in your booklet to jot down a response to that. And this is Mr. Stark signing off. Thank you so much for watching.